All right, welcome back. So let's continue. Now we are going to discuss another important concept, controllability. So whenever we want to design a control system, we better first check whether the system is controllable or not, so you do not waste time on uncontrollable systems. So what do we mean when we say a system is controllable? Let's take a look at an example of a controllable system in the real world, and that will give a sense of about the meaning of controllable.
Semi-final one.
This is our drone racing. Very fast now.
6 up and away. Duncan once again first through the Pentagon Gate. Jet and Red right behind him. They'll climb to the Sky Gate. Jet and Red making a push for that first spot.
He's going for it. Watch him do his technique. He said he wants to take these gates little by little and gain a little ground, 1 inch at a time. He's going to try and do that here.
This is the switchback. They come out of it. Duncan with a better acceleration, but Jet closes the gap as they cross over to the right side of the field. It's Duncan in white, Jet in red. 1-2. Fluxy clawing his way back into this one, and Nurk's there as well.
Look at Jet, just little by little, reeling him in. Nurk's making a move.
It's Duncan in the lead through the Sky Gate. Fluxy right there.
Jet pressing.
Remember, if Duncan wins, he'll book his spot in the final. Jet needs a win as well. Here we go. The switch back another time, and Jet's moved to the lead.
He's got it, Greg. He's found his way to the front. He cannot let up. These guys are right on him.
Jet's got clean air around the right field pole. That sweeping left turn through the Pentagon Gate.
Here comes Fluxy.
Oh, and Fluxy's trying to steal this one.
Oh!
Jet takes it back.
Yes!
Jet is going to the finals. What an amazing finish.
So you can say that are those drones or the UAVs controllable? Of course, right? Of course. Now that will give us sense, but mathematically, when we say a system is controllable, in that video, I can show you can make the UAV go anywhere. Of course, very fast, right? And for a system, we say is controllable. We say, is it possible to steer a system from any initial state to any other state in finite time? Okay, so that if yes, then we say the system is controllable. Okay, so therefore, literally really cannot say okay, controllable means that you can make the system to whatever you like. No, so here we give you a mathematical definition, right? You can make the system, right, move from one position to another, fine. You can make it to, but in finite time, right? You cannot guarantee how fast, right? You can make it to do it. But as long as you can make it, right, in finite time, then we call it controllable. So visually, you can say, okay, I have a system, right? Start from any initial point, x0, and then I want to go to a destination where I have a target position to go. So how am I going to go there? Of course, we say that the state can be driven by the input, right? That input, so apply the input. Then U0, you go to x1, you apply another input U1, you change to x2. You can see the state will be driven by the input. And of course, if you can coordinate the values of the input, eventually in finite time, you can say you can get there. If that you can be done for any initial point to any, destination, if you can make it happen in finite time, then it is controllable. Right. So that is a general definition. In that video, we said actually you has to be fast, right? You want to be the winner, has to be fast. But here the speed is not the issue. I don't care how fast you can go there, as long as you can go there. then it is controllable. Okay? All right. We know that to check the controllability, right, for nonlinear system is not easy, but for linear system, we can do it. Let's just do it here in the class. Let's do it together. Okay, we have the model. We know the model, right? The state, right, which depends upon the current state, right, depends upon the input, right? Those are the matrix and vector, phi, gamma, and also we know the output is related to the state. Of course, the state vector, right, is n-dimensional, but in this course we only consider one input, so the input and output are all scalar, one-dimensional, single input, single output. Let's start with the initial state x0. Then the state at the first step of x1, right, we get phi x0 plus gamma u0. The state at the second step, which does a simple calculation, by phi x1 plus gamma u1, and then plug in the expression of x1, right? Here is phi x0 plus gamma u0, we replace them, we organize, we get phi square x0 plus phi times gamma u0 plus gamma u1. So it depends upon the initial state, depends upon the two input signals we applied, right? The first step and the second step. Then the state at the nth step, right? We can just follow those equations. We can easily, right? We can easily obtain the expression that the state at the nth step depends upon the initial state, depends upon all the input signals applied during those whole process. For this, because we start from x0, we calculate xn, right? There are n input signals applied, right? And you can say that this is a vector by phi to the power n minus 1 gamma. That is a vector times u0, phi to the power n minus 2 times gamma. That is another vector, but u1. Remember, those input signals are scalar. So this expression just says that the state at the nth step depends upon the initial state, depends upon all the input signals. But how you compute that is just this one, right? The initial state. The other ones, all those are the vectors, is a linear combination of all those vectors, gamma, phi gamma, right, up to phi to the power n minus 1 gamma, right? And the weights of those linear combinations, right, you can choose. Those weights are the input vector. Let's rewrite the equation into a more easily visualized form, such that we can put the state together and the input signals on the right side. Remember, what we want to solve is the problem whether we can choose the input. We can choose the input to make the initial state go to another destination, right, or a desired state. So give any x0 and any destination x star, is it possible to find the control sequence u0, u1 to up to un minus 1, the n control signals, such that the state at the nth step reach x star? Let's try to solve this one. Then it becomes an algebraic problem, right? So we take the problem as solved, which means xn equals x star. Then on the left side is x star minus, right, phi to the power of x0. On the right side, we use a matrix to represent, because here you can see those are the n vectors, right? Gamma, phi to the power n minus 1 gamma. We put them together as a matrix, and those are the weights, right? Therefore, we put them as a vector u. This way, right, we can write it in a matrix WC times the vector. This is the input vector, which contains all the input signals. Is that clear from linear algebra? And then we ask the question. So once we are here, then we can ask the question, what is the condition? So we given x0, so on the left side, they all is a vector, right? On the right side is a matrix times our input vector. The input vectors are the signals we try to find. So it's a typical algebraic equation, right? In terms of a matrix equation, AX equals B. So what's the condition on this matrix such that the solution exists? What's the condition on this matrix? It has to be non-singular or it has to be invertible, right? So the controller, then actually we define this WC as the controllability matrix. This matrix has to be non-singular. You can see that, right? All the steps are very clear. You can derive it and you can get the condition. Any questions? Now, we solve this problem, right, from our algebraic point of view. We formulate as an algebraic problem. And then, but now we try to look at this condition from another point of view. That way may give you a better sense about the meaning of this controllability matrix. Let's consider a second order system, which means that the state vector is in a two-dimensional space. Let's make it simple. Assume the initial state is 0, right? Then the final state is x star. How do we make the state from 0 origin to x star? Okay, from the origin x0, I want to drive this state to x star. How do we choose the control sequence? Can you get there in one step? Can you apply one input to make this x0 go to x star? Yes or no? Visually, right? Visually, let's say gamma is this direction, because x0 is 0, right? So the 5 times 0 disappear. We only have gamma times u0. Gamma is in this direction no matter what you choose the u0. Can you make x0 go to x star? Impossible, right? Unless x star is in the same direction of this gamma, right? So therefore, impossible. So we need another step of control. Okay. Then we apply the second input. So therefore we have x2 equals 5x1 plus gamma u1. Now we replace the x1 by the gamma u0. We get 5 gamma times u0 plus gamma u1. Therefore, when we apply our input, right? When we apply input, essentially, right, we change the state with a new direction. This direction of movement is added is 5 gamma. Originally, we only have gamma, but now we have the 5 gamma, right? If I apply, you have a 2 input. Now, let's say, so therefore, you just look at this equation. So we want to go to the x star, right? X star. Now I have 2 directions to go, gamma and 5 gamma. And then because you can't choose any u0 and u1, right? You have 2 directions, and then you can change the weights, right, for each direction. Now, is it possible to drive x0 to x star now? Yes, right? Yes, easily, right? Easily you can do it. You choose x0, you will move along this 5 gamma, and then choose x1. Then you go there. Because you have 2 independent directions to go in a 2-dimensional space. You can go to anywhere, right? But of course, there is a condition that this 5 gamma has to be a new direction, right? Has to be an independent direction from the first direction gamma. Okay? You can go anywhere on the plane if you have can move with two directions. So geometrically, that is clear. Then we need to idealize, right? Because that condition, gamma and phi gamma should be independent. But what if phi times gamma is also along the direction of gamma, which means, phi times gamma is just in the same direction, right? So therefore, it's A gamma in the same direction. If that's the case, visually, right, can you drive x0 to x star? No, right? Can we reach the final in 2 steps? So we need a new direction of movement, right? Then let's try another step of control, because we say it's not necessary 2 steps, right? Infinite steps, if we can go there, then it is controllable. Let's try another step of control. Apply U2. Okay, so U2 is phi x, then we get x3 is phi x2 plus gamma U2. So therefore now we have 3 directions, gamma, phi squared gamma, right? So therefore we add another direction of movement, which is phi squared gamma. But we need to verify. Is phi squared gamma really a new direction? Well, this one can easily check, right? Phi squared gamma is phi multiply phi gamma, but phi gamma is A gamma, right? You do this, actually it's because gamma is kind of an eigenvector of this phi. So you get actually phi squared gamma is still in the same direction of gamma. Is that clear? So phi squared gamma is still along the direction of gamma. For second order system, we have shown that, right, if gamma and phi gamma are not independent directions, then the system is uncontrollable, no matter, right, how many steps of inputs are applied, you can only move in one direction. Okay? Any questions? So therefore, the controllability matrix, right, in the second order system example, consists of 2 directions, gamma and phi gamma. They provide the directions for the state to move. Okay? So if the directions are independent, 2 directions are independent, of course, we span the whole space. You can go anywhere. Then we show that actually this condition is not only sufficient, but also necessary. Now let's consider the general case, right? For nth order system, we know, okay, if you look at controllability matrix, it consists of n vectors. Starting from gamma, you have phi squared gamma, up to phi to the power n minus 1 gamma. They give you the n directions that the state can move in the state space. If the n directions are independent, of course, the n directions will span the whole space. The state can go anywhere. Right? Is that clear? So therefore, what is the meaning of this WC? That provides you a set of directions for the state to move. However, right, if the n directions are not independent, are dependent, which means there must be some directions where the state cannot go in n steps, because n give you n directions. There some of them are dependent, right? So therefore, it cannot span the whole space. What would happen? Then we have to apply more steps of control, hopefully to generate new directions. But how about one more step, right? If we apply one more step of control input, actually we can generate a direction, which is in addition to phi to the power of n minus 1 gamma, we'll have phi to the power of n times gamma. Okay? But then we have to verify, is phi to the power of n gamma are independent direction from this whole set, the original set of n directions. We showed that, but answer should be no. For the second order system, we showed it, right? If gamma and phi gamma are dependent, then this phi square gamma will not be a new direction, right? Okay. For that one, it's simple because it's gamma is just an eigenvector of phi. But how do we prove it for the nth order system? Or let's put it mathematically in a different way. So algebraically, giving a matrix, any matrix phi, square matrix, how is the power, right, phi to the power of n related to its lower powers, phi square, phi cubic up to phi to the n minus 1. That is one of the most important theories in linear algebra. In algebra, there are many theories. This one, I know, but probably already forget. But here, for the control theory, right? Linear algebra, of course, has many applications. For control theory, this is one of the most important theories. We call it the Cayley-Hamilton theory. What it states, put it simply, is just the matrix satisfy its own characteristic equation. What is characteristic equation? For any matrix phi, its characteristic polynomial is defined as, right, the determinant of this matrix, z times the identity matrix minus phi, then you get a polynomial, right? Polynomial. That is the characteristic polynomial. And also, if you put this characteristic polynomial equals 0, the roots of this polynomial will be the eigenvalues, right? The eigenvalues satisfy the characteristic polynomial. That is by definition, but of course, what the Cayley-Hamilton theory says, okay, not only the eigenvalues, the matrix itself satisfies this equation. Okay, how to prove that? Look, I don't have time, but the proof also is not trivial. But you can take a look. If you forget, you can take a look. It says for matrix, square matrix, you get its characteristic polynomial. And if I put z as phi, this is what I mean. The matrix satisfies its own characteristic equation. So I put this phi into this, that will be 0. And also we know, of course, the eigenvalues satisfy this, while here we say the matrix itself satisfies that. Okay? Any questions? But of course, this is one, when you learn linear algebra, this is a simple way to state. But if we look at this equation, right, if you look at this equation, there is another way to state this theory. It says that phi to the power of n is a linear combination of its lower powers. Is that clear? So therefore, any higher powers, of course, to the phi to the power of n. How about phi to the power n plus 1? They're also, right, if you do it iteratively, that all the linear combinations of these lower powers up to phi to the power of n minus 1. Okay? Any questions? I just rewrite this equation in this form. You look at this theorem from a different point of view, but then we are going to use this. So phi to the power is a linear combination of its lower powers. Now let's apply this. Therefore, we multiply this gamma on both sides to the right side, left side, right, gamma, right? And here we multiply this gamma. Now you can see that this direction, right, phi to the power n times gamma is a linear combination of the set of n directions. Is that clear? How do we prove that? This is by the Cayley-Hamilton theorem. Okay. So therefore, now we answer: is phi to the power of n gamma? Is it possible for this to be a new direction? Impossible. It is a linear combination of the set of n directions you already have. Okay. Therefore, no matter what you do, if the original set cannot span the whole space, the other control input will not help. Okay. So phi to the power of gamma is not an independent direction. So what we conclude is that this WC, that set of vectors, right, it has n directions. It provides all the possible independent directions that the state can move. If it cannot span the whole space, then the system is uncontrollable. There is some state you cannot go. All right? Any questions? Now, then let's talk about our controllable canonic form. So basically, we want to know, is it possible to transform a system into a form which is easier to design the controller? So we're going to use it tomorrow, right? But now let's just introduce this form. We call it the controllable canonic form. Assume a system has a transfer function. Of course, this one, right, this polynomial is the correct polynomial of phi. Then, to form the controllable canonic form, we just take the coefficients in the denominator. There are n coefficients, right? We put a minus sign on all of them, okay? And then that will be the first row. Then how about the other rows? The other rows are completely fixed. So no matter what the system is, they are the same. The only difference, right, between the different matrix phi will be here. The difference will only be reflected in the first row. The first row are taken from the correct polynomial. Okay. The other rows are all the same. The second row is all either 1 and the other elements are 0. Then this one is 0, 1, or 0. Then this control vector, this gamma right here, this one is a unit vector. The first one is 1, the other ones are 0. Okay. This is what we call the controllable canonic form. So only the first row is related to the specific system. So this first row, we call it the non-trivial row. The other rows we call trivial rows because they are completely fixed. They will be the same for all the system. Okay, so the only difference lies in the first row. That's what we call the non-trivial row. Now let's first give you the definition, but you may wonder why this one will be, if a system, right, is in this form, why it will make the controller design easy. Easy. Okay, this is algebraic form, right? Okay, let's put it in the graphic form. Then you can easily understand. You can easily understand. So how do we put it a graphic representation? Now here, look at this equation. Let's put load. There are n nodes. Each node corresponding to the state vector, right? There are Z1, Z2, up to the n, right? There are n state vector. Let's look at the first one. The z1 k plus 1 will depend upon all the values, right, of the z1, zn. So this is what I show, right? Z1 will be affected by Z1, Z2, Z3 up to Zn. That is the meaning of the first equation. And of course, it will also be affected by the input. Is that clear? You just look at the first equation. Huh? That's the meaning for this Z1. Then how about Z2? Look at the second equation of this controllable canal. Z2 K plus 1. Here, Z2 K plus 1 equals what? Z1K, right? Z2K plus 1 equals Z1K. Here, which means Z2, right, equals only affected by Z1 and nothing else. And also, which is true for the others, Z3 equals Z3K plus 1 equals Z2K. Because of this special form, that will make it easy. You can see that the input, right, the input only affect the first state variable, Z1. Then the other state variables are related to each other in a very special way, right? Z2 equals Z1, right? Z3 equals Z2, Z4 equals Z3. Of course, there is a time delay. Okay, but anyway, they are related. But they are related in a very special way, such that if Z1 are controlled properly, the other signals will follow. Therefore, the problem, we converted the problem of controlling the n state variables into controlling only one state variable, x1. That simplify the design. Okay. Any questions? We are going to use this not next week, tomorrow. Tomorrow we are going to have a class. We're going to use this controller kinetic form. Basically, right, just say that in this form that you only need to use the input to affect change one state variable. You don't need to consider the other state variables. They will follow. Okay. Now let's move on to talk about another important concept, observability. So when we have a system, we have the input and output information. Remember, right? The system may have many state variables. What are the outputs? The outputs are the signals we are measuring. We have the sensors to measure. But there is a question: is that we need to estimate, or we need to predict all the state vectors, all the state variables. But can we use the information available, the numbers, right, from the sensors, which are output, and also, of course, we know the input. Can we reconstruct the state variables from the input and output signals, which has a lot of applications in the real world problems? Because in many problems, you don't need to put a sensor to measure all, right? Because the state variables are related to each other. If you know the equations, probably just a very few number of sensors can help you to compute all the state variables. That will save the cost of the whole system. Okay, but mathematically, right, we want to solve this problem. Can we determine the state from the observations of inputs and outputs only? If yes, then we call the system observable. If no, which means some of the state variables cannot be reconstructed, cannot be computed from the output information. If that's the case, you would better try to get another sensor, to get more information to do it. But this is also not easy question. In general, for linear system, we can also find out a simple answer. We know the model, right? Now, remember the problem is that we want to estimate, we want to compute the state. Let's make the derivation simple, right? Let's assume that all the inputs are 0. We just observe the output for n steps. We know that the output, the first step, right? Let's start from the initial state. Then we have the first output signal. We measure that, which is c times x0. The second output, well, we measure that with c times x1. But x1, remember, the inputs are 0, so the x1 is at 5 times x0. The y2 is say x2, so we can say 5 squared x0. Then, so we measure n of them. So the last one is n y n minus 1 is say x minus 1 is say 5 to the power of n minus 1 x0. So we have those n signals, output signals. Now we try to compute what is the initial state. So this one, we just collect all the equations. Right, and this one, all the output signals, we put them into one column vector, right? And then this one is first one is c times x0, the second one is c phi x0, right? Those are the row vectors, right? We put them into a matrix times those x0. That put it into a matrix equation. We have a matrix times a vector. This is the vector we want to find. Those are the output signals, the signals available to you. We want to compute x0. And now should be obvious to you, right? Should be obvious to you. What is the condition? Such that you can find the solution. What's the condition on this matrix? It has to be non-singular, right? It has to be invertible. So the state x0 can be obtained if we call this one as the observability matrix. Now, of course, this matrix is different from the original controllability matrix. Controllability matrix will have gamma, phi times gamma, right? And then phi squared times gamma. And here we have this matrix, which starts from C. Now we have to multiply the phi on the right side. C times phi, right? The last row is C times phi to the power of n minus 1. So this matrix we call the WO, after the observability matrix. And this matrix has to be non-singular. Then the system is observable. Remember, we want to estimate the state vector, but from this observation, we can already compute x0. Once we have this x0, we can compute, right, all the state vectors. Is that clear? Therefore, we have shown that if this observability matrix is non-singular, we can compute all the state variables from the information on the input and output. Okay, any questions? Now, once again, we also want to look at those observability matrix from the geometric point of view. Remember, for the controllability matrix, right, that provides you a set of directions for the state to move. But for the observability matrix, it also has n vectors, right? What's the meaning of those n vectors? Do they provide the directions for the state to move? Of course not, right? Here, our concern is not about how we can make the state move from one position to another. What we are caring about is whether we can extract the state information from the output signal, okay? Now, let's first look at this equation, right? Y0 is C times X0. C, right, is a row vector. X0 is a column vector. A row vector times a column vector, of course, give you a number. But in other words, that is the dot product of two vectors, right? Dot product of two vectors, C and X0. Now what's the geometrical meaning of this dot product? What's the geometrical meaning of dot product of two vectors? Projection. Very good, huh? So basically, right, let's say you have a vector, right? Dot product with another vector. Let's say the another vector is a unit vector that is simply the projection, A times U. It's just the projection times this one R times cosine theta. It's just this one, projection of one vector. So it is defined as the projection of A on the unit vector U. So in general, right, we have two vectors. Now this Y0 is the dot product of C and X0, so which means Y0 is the projection of the state vector on the direction C. Okay, is that clear? Any questions? Okay, now then again, let's assume the inputs are 0. We observe the output for n steps. So the first output we measure that, right? The second output is C times X1, but say X1 is related to X0 becomes C phi. So here Y2 is say X2 equals C phi square X0. Then finally the Ym minus 1 is say Xm minus 1 is the C phi to the power m minus 1 X0. You can say the first output is the projection of X0 on the direction C. The Y1 is the projection of X0 on the direction C times phi, right? And then this is the projection of X0 on the direction C phi squared. Okay. Therefore, what are the outputs? The output signal are just the projections of the initial state on different directions. Okay, so the outputs are the projection of the initial state, but at different steps, then they just the projection of the same vector but along a different directions. Here, a different step, they give you the expression of those directions. Is that clear? So therefore, this observability matrix provides all the possible projection directions for the initial state vector. For n-dimensional vector, if you know its projection on n different independent directions, can you reconstruct the original vector? Right. It's like, right, you have a two-dimensional vector, you know its projection on A1, A2. Two axis, that's the projection, right? Those coordinates are actually the projection on this vector X1 axis. A2 is the projection, right, on the Y axis. You load those two numbers, of course, you get the original state vector. Okay, so if the vectors in the observability matrix can span the whole space, the information of the state can be completely recovered. Okay, so that is the geometrical meaning of the observability matrix. It is the projection directions for the state vector. If it spans the whole space, then I can construct, right, the information about the original state vector. Okay? Any questions? Okay, now let's consider the case, right? What will happen if the observability matrix WO is singular? If W is singular, it means there exists a vector, right, such that this WO times V equals 0, but that vector is not 0, which means, right, there your all the projections, if they do not span the whole space, there is a direction such that the projection of that direction among this whole space, they're all completely 0. It's like, right, all the vectors here in the plane, but you have a vector right in another direction, and they project this one along. All the vectors in this plane are all 0, right? If that happens, okay. But algebraically just says, okay, this one, for a non-zero vector, this can happen. There is this one vector which can make this equal to 0. But what does that mean? Okay. It means, right, I have an initial state, x0. I have another initial state, which is different from x0. So I add this v to x0 plus v. I multiply them because WO times V equals 0. So this will be the same as WO x0, right? In other words, what is WO, right? Here is WO times x0, you get a output signal. If I do the same thing, or WO times x0 plus V, then I also get the same output. I have a system that starts from different initial point, but by observing the output, I cannot tell which state vector is operating, right? So you cannot differentiate the initial state x0 from x0 plus v by observing the outputs. So we cannot reconstruct the original state. Well, but you may argue, right? You may argue, hey, how about we make more observations, right? Here, we only make an observation. Probably, right, the next observation will give us some hope. That will be different. Okay, let's just try to make one more observation. Just make one more observation for those two scenarios, right? So yn equals c times xn will be c 5 to the power n x0. For this one, right, y prime n is cx prime n, right, with this initial state will be, okay, this is yn. There is an additional one, c to the power n, c to the 5 to the power n times v, right, this one. So essentially we want to know, we already know that c times v, right, c 5v, they're all 0. Right? Now, if this one is not 0, they will be different. What's the value of c to the c times 5 to the power of n times v? Now, you already know with this information, can you tell me what's this value? 0. From which theorem? Kelly, Hamilton theory, the Cayley-Hamilton, because 5 to the power of n is the linear combination of its lower powers. Okay, you see, that's the power of the Cayley-Hamilton theory. Based on zeros, then this one will be the linear combination of all those numbers, but all zero. So therefore, we have shown that the linear system is observable if and only if the observability matrix WO is non-singular or full rank. Okay, any questions? In other words, right, these vectors, this WO provide all the possible independent projection directions for the state vector. If it cannot span the whole space, then there must be some direction which you cannot differentiate. Okay. Now, similar to the controllable canonic form, we also have this observable canonic form. Now, this observable canonic form, now it's in this way. Those A and B are from the transfer function. If we compare, right, those A1, right, they are taken, those numbers, the first column, right, are from the denominator, and this column from the numerator of the transfer function. If we compare it with the controllable canonic form, immediately you can say the relation between this matrix and this matrix. How do we relate those two matrices? Transpose, transpose. The column vector becomes the row vector. You do the transpose. They are related. So later, actually, we're going to use this property later to solve the controller design problem tomorrow. We're going to use this. Okay. Now, how do we check the controllability and the observability given the transfer function? Let's say if you are given the transfer function, can you tell whether the system is controllable and observable? Or in other words, from the controllability matrix and the observability matrix, we need to know phi, gamma, and c. From this transfer function, can you directly tell what is phi, gamma, and c? You cannot tell, right? You cannot tell. We cannot get the WC and W unless we have the state space model, but here is the transfer function. So given a state space model, we can easily find out the transfer function using the Z transform, right? Using the Z transform, we have the formula. So now, but here there is another, can we reverse the procedure, right? So we know that many control methods are designed for the state space model, but sometimes we may only have the transfer function. So can we convert the input-output model to the state space model? This is what we call the realizability problem. Right? How do we find out the state space model from the input-output model? Or if we can find out a state space model, right? And then from that state space model, we compute its transfer function. If that transfer function match the transfer function for this system, then we call the state space model is its realization. Okay. You're given a transfer function, right? Let's say if you find out a state space model, and then you go back and compute its transfer function. If the transfer function match this one, then we call this is a realization. Of course, right? Remember, even for the state vector, at the beginning I tell you, the state vector is not unique, right? That can be transformed into another state vector. So therefore, your state space model will not be unique. The many state space model, different state space model can generate the same transfer function. If they have the same transfer function, they are all valid realizations, okay? But then there are many possibilities. We are not going to talk about, right, all the possible realizations. That's not the main point, right? But I just want to show you one way or very natural way to do it. And also how to do it. The rules are very simple. You only need to understand the rules, and then you know how to do the realization, come up, okay, with the state space model. Let's start with the simplest case. Let's say I have a transfer function, or I have an input-output model. It's a first-order system, right? So this output, yk plus 1 equals minus a1 yk plus b1 uk. Now, I want you to get a, because this is the simplest case, to get a state space model. Then what is the state? How do you get the state space model? I give you this transfer function or the input-output model. In this case, what is the state variable? Give me the simplest answer. Of course, x equals y, right? The simplest answer. The output is the state. And this is the natural choice, right? The xk equals yk. It solves the problem, right? Then we have the state space model. Of course, you see it looks too simple, but this simple example give you the one rule is the first rule. We can always choose the output signal as one state variable. Okay, that is one rule. Also, that's a very natural choice. Why don't you want to do that? Well, I have the measure signal. I use that. That is my state variable. Okay, very simple choice, right? This is the first rule. I want you to remember. But of course, this rule may not be sufficient. Let's look at the second example. I have a second order system because the output, right, depends upon the past two outputs and the past two inputs. Now let's apply the first rule. We define the state vector x1, k, as the output signal, right? Use this rule. And then what we have? Remember, once we have the state vector, the state space model, right, is in the form of xk plus 1 equals phi xk plus gamma times uk, right? The future state, the next state, depends upon the current state and the current input. To get the state space model, I have to come up with a model. I have to compute the state at the next step. So we compute the state at k plus 1. So x1 k plus 1. But of course, xk plus 1 is just yk plus 1. I use this equation, giving you minus a1, yk is x1k. Now this minus a2. I didn't use x1 k minus 1, right? I still use the yk minus 1 for a reason. Remember, right, because in the state space model, we say xk plus 1 depends upon current state xk. There is no xk minus 1 in that equation, right? So therefore, so this one, because it is k minus 1, so I keep the yk minus 1. But here is b1 uk fine. I have a b2 uk minus 1. Okay, let's just organize those terms on the right side. we have this x1k plus 1 equals minus a1 x1k plus b1 uk minus a2 yk minus 1 plus b2 uk minus 1. Now we compare it with the standard state space model. This is the standard form. It has to be in this form. Okay, the x, the state at the next step depends on my current state and the current input, right? And also this are based the definition of the state. What is the state? That is the information can predict the whole future, right? So the next depends on my current xk. Okay. There is no xk plus minus 1, right? Because the state is the information sufficient, right? I don't need the other information. Otherwise, right, it will not be the state. So we know in the state space model, there is only on the right side, there is only current information. There is no past information. Okay. But if you look at this equation, it has some past information, right? Then we have to come up with a way to deal with the terms in the past. Okay. How are we going to deal with the terms in the past? Can you come up with a simple way? Here, I use one state variable. Use one state variable looks like it's not enough, right? So I use one more. How do we define the next one? I use the state variable to summarize all the past information. Okay? I put everything as one, everything else, right, in the past as one state variable and say whether it works. Okay. So here is where we are. We use the first state variable as the output, right? And then we have an equation. We try to compute the future state. Then we have an equation which contains some past information. And we need to deal with that because in the standard state space model, there is no k minus 1, right? There is no k minus 2, right? So to deal with that, it's very easy. I just add a new state variable to summarize all the past information. And also the important thing is that, okay, you are saying, do I need to use two state variables, one for x, y, k minus 1, one for k minus 1? No. You summarize everything and put them a lump sum into one. That will simplify the model. Okay, so therefore, I just define another. This one, like I said, I put everything together into one state vector. If we do that easily, right, this equation, right, will be consistent with the standard model, right? Therefore, we have x1k plus 1 minus a1xk plus b1 uk, about everything else, I put x2k, right? But, right, let's compute. So this one is okay, right? On the right side, only has information at k, nothing in the past. Then we need to compute x2k plus 1, right? x2k plus 1 here is minus a2yk, fine, plus b2 uk. But what is yk? Of course, yk is just x1k. Okay, is that clear? So therefore, if we reorganize the terms right into a matrix form, we get xk plus 1. This is phi. This is gamma. We have a state space model. Of course, from this state space model, we can go back and verify whether we can get this input-output model. It has to, right? Because we come from the input output model directly. Okay? Any questions? So there are two rules we have learned. One is the first rule, we can always choose the output signal as the state variable. And if you encounter some past information you want to represent, you just start with a new state variable whenever necessary. Okay? And with those two rules, you can easily solve the realization problem for all the possible scenarios. Let's just try one more example together on third order system. Why third order? Because okay, the transfer function, the denominator will be a third order polynomial. So in other words, the output depends upon the past three outputs and past three inputs. Okay, now we want to find out its realization. Let's do the lateral way. First rule, rule number one, we define x1k as the output signal. Okay, then we can let's compute its future state, right? x1k plus 1 will be minus a1 x1k, right? Minus a2yk minus 1 minus a3yk minus 2, b1 uk, this one, okay, b uk minus 1, uk minus 2. Let's put it in this way. So this one x1k plus 1 equals, depends upon x1k, depends upon u1 uk, it also depends upon yk minus 1, yk minus 2, uk minus 1, uk minus 2. Therefore, now easily you can see how we're going to deal with those past information. What should we do? I do it step by step, right? Apply the second rule. I add a new state variable, take care of all the past information. Okay? So we get x2 equals everything else minus a2 yk minus 1 minus a3 yk minus 2 plus b2 uk minus 1 plus b3 uk minus 2. Then that will take care of this equation, right? x1k plus 1 will be minus a1 x1k plus b1 uk. Now everything else, I just put one state variable, x2k. So this equation looks fine. But then how about x2k plus 1, right? So let's compute x2k plus 1. x2k plus 1 equals minus a1 a2 yk minus a3 yk minus 1 plus b2 uk plus b3 uk minus 1. Now we know this minus this yk is x1k, right? So minus a2 x1k plus b2 uk. But we still have some extra information in the past, right? Minus a3 yk minus 1 plus b3 uk minus 1. The first equation about x1k plus 1 looks fine. But there is still some problem with the second equation, right? x2k plus 1 depends upon the x1k uk, but we have some unsolved problem, right? We have some extra past information. Then what should we do? Whenever you encounter the past information, you just define another state variable, right? So you define a new state variable, introduce another state variable to summarize all the information in the past. Then let's compute the equation again, right? We have x1k plus 1 equals, depends upon x1k, x2k. x2k plus 1 depends upon x1. Now we have x3, right? And then plus u. So x1, x2, that looks fine. Then how about x3? So let's compute x3k. So x3k plus 1, right, equals minus a3 yk plus b3 uk. But yk is just x1k, right? So now everything looks okay now. On the right side, we don't have information in the past, right? We don't have k right? There is no k minus 1, k minus 2. If we put them into a matrix form, we get xk plus 1 equals this matrix, right? This is minus a1, 1, 0, right? The second one, minus a2, 0, 1. The last one, right, minus a3, the other one, 0. Then this UK, right, is b1, b2, b3. Now, if you look at this, just look at the form of this equation. It is in one of the canonic form. So which canonic form is it in? This is the observable canonic form. So what I just show you is that for any transfer function, right, we want to solve the realization problem, but we also know that the solution is not unique, but we just want to find out the natural one. And the observable canonic form give you the natural realization of any transfer function. Okay, and the beauty of this realization is that all the state variables are clearly defined by the input-output signals. Okay, so x1k equals yk, x2k equals minus a2yk minus 1, right? Then here, right, up to yk minus n plus 1, then x3k, then they're all the well-defined equations. And if you define the state variable in this way, you will have this observable canonic form, which is the realization for this transfer function. Okay? Any questions? All right. There are other ways, but okay, I don't have time to talk about that. But among all the possible realizations, observable canonic form is the simplest one, and also the natural one. The two rules are very important. You can always, if there are in the model, how do we deal with the past information? Use a state variable to summarize. Okay. So with that, that will be end for today's class, and with today's class, you should be able to finish the problems for the first homework assignment. Okay. Tomorrow, we are going to remember. Tomorrow we are going to have a class here at 6 o'clock, which is the makeup class for the last Friday. Then we were going to discuss the first controller design. Thank you. I will see you tomorrow.